Hello, and welcome to this secondary snack. My name's Ian Davis, and I'm the Head of Curriculum at White Rose Maths. And today, I'm going to be talking to you about our Year 7 spring term block, Fractional Thinking. Here are the small steps for the block. The one I'm going to be focusing on mainly is this one, adding and subtracting fractions with the same denominator. That's a key step that has many links to the steps that follow, and I'll touch on some of those as well as the last step in the block, the higher step, adding and subtracting simple algebraic fractions. For those of you who aren't familiar with our steps, this is how they're set out. We have a notes and guidance section to tell you the content of the step. We have key vocabulary that we would expect students and teachers to use in the lessons, key questions to use during and after the teaching to assess understanding of the step, and some exemplar questions that you can use in your modelling and practice. These are available as a free downloadable PowerPoint, so you can edit them to suit your own class's needs. I'm going to be focusing mainly on the first exemplar question from this step, the keyword whole, and the key question, how many somethings make a whole. Before I do that, here's a reminder of our key representations page. We have this at the start of many of our blocks, giving ideas of things you might want to use in the classroom to represent the abstract mathematics we're talking about. So some of the things here in the fractions key representations are bar models, number lines, emphasizing that fractions are just numbers and part of the number system, and using fractions as bar models and number lines together. So there I can see 4/5, I can see the whole, and I can see the whole on the number line as well. So going back to that key question, how many somethings make a whole? Many times I've said to students, how many halves make a whole? And they tell me confidently, it's 2. How many quarters make a whole? It's 4. How many sevenths make a whole? And I get much less of a positive reaction. Many of them have no idea and can't make the link to this abstract fraction, sevenths, that they don't see very often, the way that they see halves and quarters in everyday life. They don't understand the structure of fractions and that sevenths means 7 equal parts in the whole. So one way of supporting this is through bar models. So in our first exemplar question, when we're adding simple fractions with the same denominator, we've got it modeled, set out for them, 2/7 and 3/7, and then they can see that the total shaded is 5/7. The second part of the exemplar question, we do the other way around. We give them the whole, all of it is shaded in, and they need to complete the statement that matches the picture they are provided. Then we remove that scaffolding and ask students to provide their own pictures to work out some other questions. Notice that for one of them, we're dealing with 20/3. So this leads to a good discussion as to when do you need to draw a picture? When is it useful to do a picture? This one, it's a subtraction, so you don't need to show all 23 parts in the whole. And even if it were an addition, drawing all 23 parts is inefficient. So hopefully we'll begin to generalize and remove the need for the scaffolding of the pictures eventually. Another way of showing how a whole can be split up is a part-whole model, which we use in many aspects of the curriculum. Again, we've got a question about sevenths, showing how they can partition the sevenths in the whole, but you could edit this into 11ths, 15ths, etc., helping the students to make that generalization about how many there are in a whole. Now let's move on to adding and subtracting fractions. Here's a common way of representing a calculation like 6/7 add 4/7. Here's my 6/7. For the 4/7, I can't fit them all in, so 1 needs to go there, and then 3 needs to go there. However, many students can misinterpret this representation to showing 6/7 add 4/7 is equal to 10/14. because there are 14 equal parts and 10 of them are shaded in. Again, we really need to emphasize the idea that each bar here is a whole. So that's one whole. That whole bar is a whole, but we've only got 3 of the sevenths shaded in. So altogether, I've got 10 sevenths, and it's one whole and 3 sevenths. Another way of representing that would be to have the bar model alongside the number line. So again, the number line is going from 0 to 1. I can show 1 seventh, 2 sevenths, and the important fact that 7 sevenths make a whole. And also, the number line can go beyond 1. Students are familiar with number lines in integer contexts, so using them in fractional contexts will help understanding that when we're doing this calculation, 6 sevenths, add 4 sevenths, I can start with 6 sevenths, add on the 4 sevenths next to it, and I can see I've gone beyond one whole. I've gone to 10 sevenths, and that is equal to one whole and another 3 sevenths. Here are some more questions involving adding and subtracting fractions with the same denominators that link to the whole. These ones are from our premium resources. Have a look and see what you think. Pause the video. In part A, we can see that the answer is a whole, emphasizing that point. For part B, there is a whole needed in the second part of the question. And in part C and D, we need to do some reordering in order to find the wholes and be able to answer the questions more easily. We've also tied in and interleaved algebra, which we taught at the beginning of the year. We've got y plus 7/12 is equal to 1, again emphasizing the relationship to a whole, but doing it in an algebraic context. In our higher step at the end of the block, we look at algebraic fractions. If students have got a good understanding that 5/5 are a whole, 7/7 are a whole, then they should also understand that x/xths are a whole and y/yths are a whole, even though they sound a little bit different. Moving on from the main step, we then look at subtracting fractions from that whole. Again, making that relationship clear so that students can apply it with mixed numbers later on, and also in calculations subtracting from larger integers. Here's some questions from our mixed numbers steps. Just pause the video again for a second and have a look how important the whole is to understanding and accessing these. Again, we can see in Rosie's method, you need to understand the whole in order to be able to produce the improper fractions. And in Mo's method, you need to understand the whole and being beyond the whole to perform that final subtraction. So in summary, a bar model is a really good way of representing fractions, but we do need to always relate it to the whole so students understand what the whole means. Number lines are great for supporting this, and we can put 0 and 1 in different positions to represent different fractions, and also even if you want to include the idea of negative fractions. Also, remember that a fraction is a division, so 3/5 as well as 3 equal parts of 5 in a whole one also means 3 divided by 5. 3 whole ones divided into 5 equal parts, each of which will be 3/5. But that's a whole other snack. I hope you've enjoyed listening to this snack, and we hope to see you soon at other snacks or at our other professional development events.